On an airplane, it's easy to pick out the other geographers who are on board. They're the ones who scrambled for window seats. I'd like to share a view where every seat is by a window, the cockpit of my trusty Cessna. Let's strike out across North America to find real examples of the landscapes you'll be studying. Places like Cape Cod and the Mississippi River, California's San Andreas Fault, and Tennessee's Smoky Mountains, the glaciers of Alaska, and cloud forests of Costa Rica. Hello, I'm Michael Collier. With these mobile field trips, we'll get perspectives from the air, land, and even underwater on major Earth systems that physical geographers study: the atmosphere, biosphere, hydrosphere, and lithosphere. We'll be looking for patterns and relationships that link these spheres together. Geography is an evolving science that, in one way or another, has always concerned itself with the processes by which landscapes and life interact. 200 years ago, geographers were explorers and map makers. 100 years later, they were geomorphologists interpreting surface features and biogeographers studying plant and animal distributions. Meteorologists in the late 20th century began to use satellite data to plot the path and intensity of storms. With 21st century technologies, those wonderful old paper maps have been surpassed by a powerful Geographic Information System, or GIS, that can be used to collect, map, and analyze geographic information. Physical geographers have always drawn inspiration and information from other sciences: geology, biology, hydrology, climatology. Now more than ever, they adapt tools from these specialties to synthesize a larger view of the world. Geographers ask, why is what where? Physical geographers pay attention simultaneously to specific local issues like land use and stream flow, and to broader issues like environmental impacts and climate change. Human geographers focus on the cultural connections between people and their environment, the dynamics of cities, and the interlinked global economy. It's not unusual for any geographer to be drawn into difficult conversations about topics like mining waste and the consequences of energy production. Physical geographers are likely to investigate the rapidly changing demographics of southwestern states, the impact of global oil prices on natural gas production in Canada, record high winter temperatures across the eastern seaboard, physical geographers would be more likely to investigate a region's weather and climate. We're over the high mountains and wide valleys that lie between Colorado's Rocky Mountains and Washington's Cascade Range. Precipitation through this region is precious, maybe 20 or 30 inches a year in the high country, but not even 10 inches in some of the low spots. Drought, with its long winters of little snow, is an ominous word to people who try to make a living here. To get started, let's look through the eyes of a physical geographer who's worked extensively in the Intermountain West. Erica Wise is fascinated by climate and storm patterns. Back home in North Carolina, she teaches courses on physical geography and climate change. Out here, she drills tree ring cores from ponderosa pines and Douglas fir. The cores reveal annual growth rings, some thick, some thin, that tell of dry and wet years. On this trip, she's working with Matt Dannenberg, who's modeling forest growth in times of climate stress. Tall tree height is often an indicator of rapid rather than sustained growth. Erica looks for old trees with unbroken records of past climate. Old pines tend to have raggedy flattened tops and smooth bark. They might have scars from fires in the past. Erica usually heads uphill to weather-beaten ridges where the trees have pronounced thick and thin growth rings that make the interpretation of past climates more obvious. The oldest ponderosa she's found so far started growing in the year 1390, more than 600 years ago. A lot of people still remember the dry, Dust Bowl years of the 1930s. Farms collapsed, animals died, ranchers gave up. But after a few generations, memories and written history begin to blur. Where can scientists find a longer view of this region's environment? The study of tree rings, called dendrochronology, is a tool that geographers have employed since the 1800s to reconstruct past climates. The Dust Bowl drought is faithfully recorded in trees that lived through the 1930s. But Erica Wise's cores reveal wet and dry periods that stretch over 6 centuries. Remember, in the West, forests and people have always depended on a steady supply of rain and snow. Armed with tree ring data, geographers can offer a knowledge of past climate patterns that are useful to anyone who wants to know what the future might hold. Sounds straightforward, doesn't it? Drill a core, count the rings, and publish the results. The story gets a little more complicated, though, when you start correlating different trees from different locations. Wise and Dannenberg are measuring oxygen and carbon atoms within individual growth rings. Erica is trying to show how stable isotope concentrations reflect the distance and direction that a storm travels inland. After cross-checking this data against similar isotope concentrations in soil water, Erica plots information from old trees scattered around central Washington. Modern-day storms follow different paths depending on regional pressure patterns out over the Pacific Ocean and the Aleutian Islands. Erica is trying to reconstruct not just past climates, but past storm tracks, something that nobody has done before in this region. Her research takes us one step closer to understanding why and how climates fluctuate over long periods of time, in the past and perhaps in the future. Physical geographers can use dendrochronology, or the analysis of tree rings, to help determine the species of a given tree, changes in climate and annual rainfall that occurred in a tree's lifetime, the density of vegetation in different regions. In areas where climates are relatively predictable, tree rings can be used to determine both short and long-term changes in climate and other environmental conditions. Who said geographers just look at maps? We try to understand our role within a landscape. Why is what where? It's imperative to know how that landscape fits together in the first place, how rock becomes soil, where water flows, why plants grow here rather than there. Physical geographers ask how and why landscapes have changed over time. They study why slopes fail and how valleys fill with sediment. They model the immediate influence of weather and the long-term effects of climate. Geographers also want to know what we're doing to our planet, and what can be done to protect it in the future. Back home, Matt Dannenberg spends plenty of time tethered to a computer, but he believes that geography students need to get out into the real world, to hike, to see, to get their hands dirty, to make a difference. Erica Wise would like to prepare them to tackle one question that she feels is terribly important. How are we humans interwoven into the fabric of our landscape? Matt Dannenberg is right. It's good to step away from the computer and come up for air once in a while. These field trips are meant to pique your interest in some of the subjects that physical geographers study. They'll try to bring you face to face with intriguing landscapes. But the field trips are still electronic, still a virtual experience. We hope you'll learn what you can from them, and then have the chance to head out into the real world on your own as a geographer.